So our force diagrams are clearly not going to be simple up, down, left, right. You're going to have forces at angles for the majority of the problems. We already looked at how to add numbers to force diagrams. Now we're going to add numbers to force diagrams that have angled forces. Essentially what you're doing now is breaking a force into its components. The angle will be the angle will be important, and it'll help you get what your x and y component is. So this is very similar to when we were doing mathematical addition of vectors in the sense of how you're going to find the x and the y component. So just to refresh, any arbitrary vector, and in this case we're going to be dealing with forces, will have an x component and a y component. And this x and y component will help make a triangle. So this could also be drawn here, making the triangle at any angle. And we're just going to use the angle theta. So when we were doing vector addition mathematically, the x component was equal to the vector times the cosine of the angle, and the y component was equal to the vector times the sine of the angle. This is no different from vector addition. All you're doing now is dealing with a force as opposed to any kind of vector. So the vector can be a velocity and acceleration. In this case, we're going to be dealing with just forces. So when you're drawing a force diagram and you're looking for the value of the x component and the value of the y component, you take the force times the cosine of the angle for the x and the force times the sine of the angle for the y. So for example, let's say we have this tension force, and we'll say it's 20 newtons. And let's say this is pulling a box. Box is moving to the left, and the tension force is at an angle of 40 degrees. Drawing this force diagram, going down we have Fg, going up and to the left is the tension force. Let's assume this is constant speed. Going up would be a normal force. Going to the right would be a frictional force. Breaking apart my tension into the x and y components, it goes up and to the left. So that would be Ftx, and going up would be Fty, canceling that out. It's moving at constant speed, so top has to equal bottom, left has to equal right. So I need to make my Fg a little bit longer to show that these two added together give me this. I don't have any values for any other forces, and that's not going to be relevant right now because all I'm looking for is my x component and my y component of the tension force. So to find Ftx, I take my tension force, 20 newtons, times the cosine, of 40 degrees. 20 newtons cosine 40, again making sure that your calculator is in degrees and not radians, gives us 15.32, keeps on going newtons. So this force right here is 15.3, keeps on going newtons. The y component of my tension force, Fty, would equal 20 newtons times the sine of 40 degrees. So this equals 20 sine 40. 12.85 keeps on going newtons. So Fty, I'll write this in a different color. 12.8 keeps on going newtons. I don't have any other information, but let's just randomly give this box a 10 kilogram mass. I can solve for the weight. Fg would equal the mass, 10 kilograms, times 9.8 newtons per kilogram. So this would equal 98 newtons. So weight 98 newtons. Because it's moving at a constant speed, top has to equal bottom, left has to equal right. So since left equals right, my tension force in the x direction would be equal to the frictional force. So friction is also 15.3, keeps on going, newtons. And the only other force left to solve for is my normal force. So normal force will equal, well, let's look at it this way. The top added together, so normal force plus Fty will equal my weight. Therefore, normal force equals weight minus Fty. That's a T. You already have weight, you already have Fty. So this is equal to 98 newtons minus 12.8 keeps on going newtons. So my normal force would equal 85.14 keeps on going newtons. So 85.1 keeps on going newtons. I realize this is messy and I apologize. I'll do another example that's a little bit cleaner and spread out. But this is how you break a force into its components and then solve out a force diagram when you've got an angled force. So I will do 2 more examples. I recommend at least watching the next one. And if you don't want to see the last one, then that's fine. But definitely watch the next one. It's slightly different than this, and I'll have it typed out. So the next 2 examples that I'm going to do, you do have in your packet where it says quantitative force diagrams with angles. I'll do both of those, and then we'll do a bunch of practice in class. This next example you already have. It's typed out on the sheet that says quantitative force diagrams with angles. And I'm going to do this one and the one after it. A chimney sweep pushes down on his broom at an angle of 40 degrees, moving across the floor at constant velocity. If the contact force on the broom by the chimney sweep is 10 newtons, and the broom has a mass of 3 kilograms, find the normal force and the frictional force on the broom. So the first thing we need to do is draw a diagram of what's happening. You've got a chimney sweep pushing down on a broom, moving across the floor. And they're moving at constant velocity. So what do we know? We know that the angle theta is 40 degrees. We also know that the contact force is 10 newtons and the mass of the broom is 3 kilograms. And we are looking for the normal force and the frictional force for the broom. So the only object that we care about for this problem is the broom itself. The chimney sweep is just what's applying the force onto that broom. The only thing, therefore, that we need to draw a force diagram for is the broom. So I'm going to start with a dot, and let's identify the forces. Based on the way I drew my diagram, the broom is moving to the right. Going down, we've got gravity. Going down and to the right is my contact force. If I had drawn this the other way, so if the broom was moving to the left, then the contact force would be going down and to the left. And this is why it is absolutely necessary that you draw a diagram to show the direction that your objects are moving, and therefore the direction of the forces. We know that going up is going to be a normal force, and broom is moving to the right, so frictional force is going to the left. My contact force is the only thing not parallel or perpendicular with my axes, so I'm going to break that apart into FCX, going to the right, and FCY going down, crossing out that contact force. And then I need to make my normal force a little bit longer. Since it's moving at constant speed, the top force has to equal the bottom 2 added together. And one other thing, the angle. So it tells us that the angle is 40 degrees. That 40-degree angle is right there. So that means that this contact force is at a 40-degree angle relative to the x-axis. No matter what, whenever we do force diagrams, any kind of components, you want your angle relative to the x. And the reason you want it relative to the x-axis is so that when you get the x and the y component, you can always use cosine for x and sine for y. So that 40-degree angle is right here relative to my x-axis. Okay, so what do we know? We know that the contact force is 10 newtons. We know that the mass of the broom is 3 kilograms, so we can very easily find the weight by taking 3 times 9.8. 3 kilograms times 9.8 newtons per kilogram gives me a weight of 29.4 newtons. Since we have the angle, we can also find FCX and FCY. And I'm going to go on to the next slide just because I'm running. So FCX is equal to the contact force times the cosine of the angle. So this equals 10 newtons times the cosine of 40 degrees. 10 cosine 40 is 7.66, keeps on going, newtons. For my y component, FCY equals the contact force times the sine of the angle. So this will be equal to 10 newtons sine 40 degrees. 10 sine 40 is equal to 6.42, keeps on going, newtons. So on my force diagram, I'm just going to resketch it. You don't have to. We've got FG and FCY going down. Going to the right, we have FCX. Going up is the normal force, and going to the left is the frictional force. Because it's moving at constant velocity, top equals bottom, right equals left. So FCX was 7.66, keeps on going, newtons, which means that the frictional force would also be 7.66, keeps on going, newtons. My FCY is 6.42, keeps on going, newtons, and my FG was 29.4 newtons. Normal force is equal to the bottom two forces added together, so Fn will equal FCY plus Fg. This equals 6.42, keeps on going, newtons, plus 29.4 newtons. So therefore my normal force will equal 35.8, keeps on going, newtons. Two things we were looking for were frictional force and normal force. We just solved for both of those. So with sig figs, frictional force is about equal to 8 newtons, and the normal force is approximately 40 newtons. And all of this we got just by using things that we've pretty much already known how to get. So getting the x and the y component of something the same way we did when we were doing mathematical vector addition, and then finding the weight. The equations that you would really need to know would only be this, and then the equation for weight. This right here, the normal force equaling contact force in the y direction plus Fg, comes directly from the force diagram. So that's why every single problem that you solve needs a force diagram, because this is not an equation to memorize. This is something that comes straight from here. Every force diagram is not going to be the same, so the way that you find the normal force, or whatever force it's asking for, will not be the same. It's going to depend on the direction of everything and what needs to balance out. I'm going to do one more example, and it's the example right underneath this one on your sheet about a box being pulled at constant velocity. A box is being pulled at constant velocity at an angle of 50 degrees with a force of 20 newtons. If the mass of the box is 7 kilograms, find the normal force and the frictional force on the box. And here's a little typo, so let's fix that. There we go. Okay, so diagram, give and find. This is a pretty simple diagram. here's the box. It's being pulled. We can assume it's being pulled by a rope, moving at a constant velocity at a 50-degree angle. Given. We know that theta is equal to 50 degrees. If we're assuming it's a rope pulling the box, we'll call that a tension force of 20 newtons, and mass of the box is 7 kilograms. We're looking for the same two things as the previous problem: normal force and frictional force on the box. So for this force diagram, I've got tension force going up and to the right, and that's at the 50-degree angle. Gravitational force going straight down. Box is moving to the right, so friction points to the left. And normal force going straight up. I want to break apart my tension force into the x and y components. So Ftx and Fty. Canceling that out. And since it's moving at constant velocity, I need to make my bottom force longer to show that top equals bottom, and then I'm going to make my frictional force also longer to show that left equals right. Okay, so my force diagram is balanced. We're looking for the normal force and the frictional force. Just by looking at the diagram and knowing Newton's first law, constant speed, balanced forces, frictional force will equal the x component of my tension force. I know that my tension force is 20 newtons, and I can get this x component and the y component very easily. Also, given the mass of the box, I can find the weight. It's just 7 times 9.8. So I know that the weight of my box, Fg, is 68.6 newtons. So my x component of the tension force will equal the tension force times the cosine of the angle. Do this over here. So Ftx equals 20 newtons, cosine 50 degrees, that's a 5. Ftx equals 12.8, keeps on going, newtons. Since we know that the tension force x component is equal to frictional force, we know that frictional force is also equal to the 12.8 keeps on going newtons. So with 1 sig fig, frictional force is about equal to 10 newtons. Now at my normal force. So force diagram, we have Ftx, Ff, those were equal. Going down, we've got Fg. Going up was the normal force, and Fty. If I write an equation for my forces in the y direction, top added together has to equal bottom. So Fn plus Fty equals Fg, meaning if we're looking for the normal force, it'll be Fg minus Fty. We already know Fg, and Fty is easy enough to find. Fty is equal to 20 newtons times the sine of 50 degrees. 20 sine 50 will give us 15.3, keeps on going, newtons. So normal force equals 68, this is a 6, 0.6 newtons minus 15.3 keeps on going newtons. So this gives us a normal force of 53.3 keeps on going newtons. 1 sig fig, my normal force is about 50 newtons. So if you'll notice, the equation to find normal force here was different than the chimney sweep problem because it was purely based on the force diagram. The chimney sweep had the y component pointing down as opposed to up, so solving for the normal force is different, and this is why I say Don't memorize an equation in order to solve for these. You have to use the force diagram. If you ever see something asking you to draw a quantitative force diagram, all that's doing is solving out for all of the forces and writing them in. So to make this quantitative, we already know what all the forces are. With 1 sig fig, this would be 70 newtons. FTY would be 20 newtons. FN, 50 newtons. FTX, 10 newtons. And FF, 10 newtons. So that's making the force diagram quantitative with sig figs. But if you ever have a problem asking you for a quantitative force diagram, it means to solve for all of the forces. We'll be doing a bunch of practice with these kinds of force diagrams where we're putting in numbers, breaking things apart into components using sines and cosines. So we'll practice with that, and then pretty soon we'll start making these a little bit harder.